Hey guys, sorry I had to be out again today. Unfortunately, my daughter got sick tonight and I have to be home with her today. So I will be back tomorrow one way or the other. So I will plan to see you then. The first thing I wanted to do today was go over the problems with you guys that you did on Friday in class and make sure you got those right and understood them. So I'm going to work through those problems for you here. And then after that, I have one more problem for you to try today, and we'll be able to go over that tomorrow, and then we'll move on. So what we see here is we have a metal loop of wire sitting on a table, and we see that we can have a magnetic field going perpendicular to the table, and it can either be going up out of the table towards the ceiling, which they've defined as the positive direction for the magnetic field, or it can be going down through the table towards the floor, which they have defined as the negative direction for the field. We also see the resistance of the loop of wire, and we also see that it's an area of 0.3 square meters. And then they give us a graph of the magnetic field as a function of time. So we see that it starts off in the negative direction down towards the floor, and then over the first 2 seconds changes from negative to 0 to positive. So now it's coming up out of the ceiling, and then it stays towards the ceiling, and then it stays constant for 2 to 4 seconds, and then from 4 to 6 seconds we see that it goes from being pointing up towards the ceiling, going back down to 0 by the time it gets to 6 seconds. So for part A, they've asked us to calculate the value of the magnetic flux through the loop at time t equals 3 seconds. And in this case, since the field is exactly perpendicular to the loop or parallel to the normal line of the loop, all we need to do for flux is do B times A. So I'll write that out and solve that. Alright, so we do flux equals the field strength times the area of the loop, so 0.2 times 0.3, and we get 0.06 Webers, or Webers. Alright, so then after that, they've asked us to calculate the magnitude of the EMF induced in the loop during the time interval t equals 0 to 2 seconds. And so remember, to calculate EMF, it's going to be the change in flux over time. So we can calculate the change in flux from the graph and then divide it by the time of 2 seconds, and that should give us our EMF, and we'll do that on the next page. Okay, so EMF always equals the change in flux over time, and in this case the change in flux comes from a change in the magnetic field. So we're going to do the final magnetic field minus the initial magnetic field, and then all of that times the area divided by time, and that should give us the EMF. So I'm going to plug in the numbers we get from our graph and go ahead and solve. Alright, so for that we get 0.2 minus a negative 0.2 times 0.3 divided by 2, and the EMF does come out to 0.06 volts. So for part C, this is where they ask us to graph our current as a function of time. So if you go back and look at the original graph given for the field as a function of time, what we'll see is that the field is changing from 0 to 2 seconds. And so there we should have a change in flux over time and get an EMF and therefore get a current. From 2 to 4 seconds we see the field is not changing, so there's no change in flux, so there's no EMF, and so there's no current. And then finally from 4 to 6 seconds we see that there is a change in the field, so there is a change in flux, so we should get an EMF and a current there. So for the first 2 seconds, we just calculated that the EMF is 0.06 volts. So now all we need to do is figure out the current and the direction. So first of all, using Ohm's law, we do find that EMF equals IR, so I equals the EMF divided by the resistance. So for those first 2 seconds, we do get a magnitude of the current for 0.3 amps. Now the next thing we need to do is figure out the direction of that current. So if we look at our graph for field as a function of time, we see that the field changes from going into the page to out of the page if we were looking down at the table. And so what happens is that then the current's going to go in a direction that wants to make more field that is going down towards the floor. And if you use your right hand rule, you will see that that current would have to go in the clockwise direction, which they have defined as negative. So for the first 2 seconds we're actually going to get a current of negative 0.3 amps. Then, as we said earlier, from 2 to 4 seconds the current should be 0. So now we're going to do Ohm's law again to figure out the current from 4 to 6 seconds. So once again, the current from 4 to 6 seconds is going to equal the EMF divided by the resistance. But before we do that, we have to calculate the EMF from 4 to 6 seconds. So if we do that, we'll get that the EMF is 0 minus 0.2 for the change in field times 0.3 for the area divided by 2 for the time. Get a magnitude of the EMF for 0.03 volts. So now we can plug in and solve for that current. So for this one, we do see that the current is going to be a magnitude of 0.15 amps, and then we have to figure out the direction again. So this time we will see that the field is getting weaker out of the page, so the current is going to try to make more field that is out of the page, and if you use your right hand rule, you'll see that current has to be counterclockwise, which is a positive value for the current. So now let's set up our graph. Alright, so as we said before, we should have a current of negative 0.3 for those first 2 seconds. We should have a current of 0 from 2 to 4 seconds. And then we should have a current of positive 0.15 from 4 to 6 seconds. And if you want to connect that with vertical lines, that will be fine as well. So hopefully that problem makes sense for you. And now we're going to move on to the second problem I gave you. Alright guys, so for this problem we have a rectangular loop of wire that has a 5 ohm resistor in it, and we see that the left half of it is currently in a magnetic field of 0.5 Tesla going into the page, and someone is taking that loop of wire and pulling it at a speed of 3 meters per second to the right. And for part A, it wants us to determine the potential difference induced between points X and point Y. We will get an EMF because we have a change in flux because we are changing the area of the field that is inside the loop when we pull it to the right. And if you'll remember, we have derived an equation for that EMF in class last week, which is that the EMF equals B times L times V. So I'm going to go ahead and plug in and solve. Alright, so when we plug in that the EMF equals B times L times V, we get 0.5 times 2 times 3, and we get an EMF of 3 volts. So then it says, in the figure above, show the direction of the current induced in the resistor. So if we look at this, as we pull that loop to the right, the flux going into the page is going to be decreasing, and so the current around the wire is going to go in a direction that makes more flux into the page. And using your right hand rule, you can see that that will have to be a clockwise current around the entire loop, and so what that means then is that the current through the resistor would be going from X to Y. Alright, so for the rest of this problem, it's going to start to ask us about the forces required to keep that wire moving, and also some questions about power. So we're going to go ahead and do that on the next page. Alright, so question C asks us to figure out the force required to keep that wire moving to the right at 3 meters per second. If you think about the clockwise current going around the entire loop, then on the left-hand wire on the loop, that current will be going straight up, and it is in a magnetic field that is going into the page. And so what's going to happen then is that if we use our right hand rule, we will then see that the force on the wire from the magnetic field has to be to the left, and so a person must be pulling that wire to the right to keep it moving to the right at 3 meters per second. So we can calculate that force by multiplying I times L times B. So to get the current, I just did the EMF of 3 volts divided by the resistance of 5 ohms, so it's 3/5 of an amp for the current, times the length of the wire, which is 2 meters, times the 0.5, which is the magnetic field strength, and that comes out to a force of 0.6 newtons. And for part D, they ask us for the power, the rate at which work must be done to keep the loop moving at 3 meters per second. So if you remember from physics last year, when you're pulling something at a constant velocity, the power required to do that is equal to force times velocity. And that's because it's work over time, but work is force times distance, and distance over time is velocity. So if you calculate that, we take our force of 0.6 newtons, we take our velocity of 3 meters per second, and we are going to get a power of 1.8 watts. Now for part E, they have asked us to determine the rate at which thermal energy is dissipated by the resistor. So that's really asking for the electrical power being used. So to do that, power equals I times V. And like we said earlier, we have a current of 3/5 or 0.6 amps. And we know we have an EMF of 3 volts. And what do you know? We have an electrical power of 1.8 watts as well. Now at first that seems like a fun coincidence, and then we're going to realize, yeah, there's a little law that tells us that that should probably be true. So in this problem, put mechanical power in as we pull that loop to the right, and we are getting electrical power out as dissipation of thermal energy by the resistor. So it is not a coincidence that those two numbers are the same. Alright, so part F says, what if we take that resistor and we replace it with a capacitor? What would the charge be? Well, we're still going to have an EMF of 3 volts, and so we can go back and just use our equation for capacitors. So, of course, capacitance is the charge built up on the plates divided by the voltage. So the charge equals the capacitance times the voltage. So we take our 3 times 10 to the negative 6th for our capacitance times the 3 volts for our EMF. And we will see that the charge built up on the plates will be 9 times 10 to the negative 6th coulombs. So for part G, that is which plate is going to be positive and which plate is going to be negative. So we know that while we are pulling that loop to the right, it tried to produce a clockwise current, and that would be the direction of the current as the plates are charging as well. Now, once that capacitor is fully charged, that current will stop, but at that point, since the clockwise current has been going, the top plate should be positive and the bottom plate should be negative, and that completes that problem. So, I hope that problem makes sense to you now. If not, I can certainly answer a few questions for you guys on that tomorrow, and I've posted one more problem for you on Google Classroom, so enjoy that, and I'll see you guys tomorrow.